1.1. All right, so estimate the slope of the line just by looking at it. Okay, so this is where we want to use that one definition. I forget who told me in class on Monday. Somebody told me that another way to think about slope is rise over run, right? The change in y over the change in x. So it's important to remember that we can visually see what the slope of the line is. Like we know that this slope is going to be negative, right? Because it's going down the hill, right? But also just remember that if you look at any 2 points, so I have a point that's right here and a point that's right here, I can estimate the slope just by looking at it visually as well. This isn't the algebraic way, but again, just a kind of a good reminder that slope is the change in y over the change in x, and that's a delta, which means change. Okay. So the change in y is that our line goes from here to here. It goes down 8 units, right? It goes down. If I want to figure out how do I get to this blue point here, it's going down 8 units. So my change is -8, right? And then once I get to the bottom here, it's going over to the right, +2 units. So I would estimate this slope to be -8 over 2 or -4. Okay, I think it's just kind of important to remember that visual, that we can do that. We can also algebraically find what the slope of this line is, right? Actually, maybe we'll go ahead and do that just to make sure. But just remember that visual. So when you're trying to figure out your rise over your run, right? Anything that's moving this way or this way, so if you're moving to the right or up, you're moving in a positive direction when it comes to slope, okay? If you're moving to the left or you're moving down, right? You're moving in a negative direction. So we moved down 8, and that's why I got a -8, and I moved over to the right 2. So it's +2, okay? This is back in your brain somewhere. Somewhere in there, right? Now, if I took the same exact problem, right, and I asked you to find the slope algebraically, could you do it? Yes, right? Or I could last year. No, I'm just kidding. You guys can do it, right?
Sure.
Sure, you can do it. That's right, Josiah, right? So here, one of our points is at 0, 8, right? And the other point is at 2, 0. So I just want you to remember that we can say the slope is the change in y over the change in x, or algebraically, we could say that it's y2 minus y1 over x2 minus x1. So we can also algebraically find the difference between the points. So you guys know me. You guys have all had me in class before. You know I like to label my points or else I forget. X1, Y1, X2, Y2. That's just me. You don't have to label them. And my X's and Y's kind of look alike when I write on the computer. But what that looks like algebraically is Y2, which is 0, minus Y1, which is 8. Okay, over x2, which is 2, minus x1, which is 0. And I end up with, big surprise here, right? -8 over 2, which is -4. So I think we've shown visually, graphically, right? We've shown that the slope is -4, and visually we've shown that the slope is -4, right? And then just remember, if you ever need to take the slope, if they tell you the slope is -4, oops, that's weird. if they tell you what that is, right, that also means that you rise -4, run +1. Rise -4, run +1. And then you end up in that right point. So just kind of an all-around review of that, right? Exciting stuff. Okay, I want to skip over here to one of these guys. Let's try number 20. Okay, so number 20 says, find the slope and the y-intercept, if possible, of the equation of the line algebraically and sketch by hand. Use a graphing utility to verify your answers to A and B. So you have 19, 21. You have 3 of these to do. So you're like, oh, sketch by hand. But this just should be a rough sketch, right, of what's going on with this graph. So let's do number 20. And I want you guys to try it too. You can kind of try it off to the side of your paper or maybe up at the top. There's a little space up there. So if you wanted to find the slope and the y-intercept of this line algebraically, how would we do that? So the way that this is written right now, we could find it, right? We could like make a little table and find a bunch of points, and that would be very fun and exciting. But does anyone know another way that we could rewrite this equation that would help us find the slope and the y-intercept easily? What's that way that we always say y equals? There we go. Greta just texted me. It says y equals mx plus b. You guys remember that? Y equals mx plus b. We talked about that on Monday, and you guys were all like, yeah, you remember that. Where m is the slope, right? And b is the y-intercept. So if we can make this equation look like this equation, then we have a much easier job of finding the slope and the y-intercept, right? So then it's just some fun algebra. It's a little algebra exercise, right? We have 2x plus 3y minus 9 equals 0. So I'm just going to go ahead and move my 9 to the other side to start. 2x plus 3y equals 9, right? So I added 9 to both sides so that I got my number on the other side of the equation. I should have went ahead and subtracted 2x from both sides. And while I'm doing this, if you guys want to be doing it, if you're working a little bit ahead, that's okay. Like, you can try the problem. If you're like, oh, I feel like I can solve this, you don't have to wait to watch me do it. So I get 3y equals negative 2x plus 9. So I'm almost there and making my equation look like y equals mx plus b. What's the last thing I have to do? What do I have to do? I got to get y all by itself, right? So I need to divide everything by 3 or multiply everything by 1/3. So when I try to do it, I do it like this. I multiply or divide this by 3, divide this by 3, divide this by 3. So when I simplify all that, I get y equals negative 2/3 x. And then what's 9 over 3? It's just 3. Okay, so I rewrote my equation, and now what's my slope? My slope is negative 2/3, right? And my y-intercept is positive 3. Okay, if I had, let's see, I haven't used Desmos in a while. Let's see, let's pull up Desmos. Who knows what that is? Desmos. I can type. There we go. Good old Desmos. You can totally do this on your graphing calculator. I'm actually going to pull up Desmos and use it as my grid, and then I'm going to see if I did it right. So if I want to sketch this by hand, okay, let's try to make it as big as possible while I still have my formula over there. There we go. Okay, so my y-intercept is at +3, so it's right here. Oh, I can't draw on Desmos, bummer. And then my slope is -2/3. So my y-intercept is right here, and my slope would rise -2, -1, -2, and run 3. 1, 2, 3. Rise -2, 1, 2, run +3. So in my mind, I know I should have a line, and if I sketch it, that goes like this. You guys see that? Well, I'm not writing anything now, but so you can't really see it. So then if I go and I check it on my graphing calculator, there we go. So here's my y-intercept, right? And here's my slope. I rise -2, run +3. Rise -2, run +3. So yay, we're smarties, right? Everybody feel like they remember this?
Yeah.
Yep. Awesome. Everybody else feel like they remember it?
Yeah.
Yeah. Okay, great. Okay, I will ask you then about the next page. So you guys let me know if you want to do an example from this. So back to our notes. Lots of notes for this section. All right. What if instead of telling you an equation that's not in the right format, oh, I like that. You nod your head in agreement. Daniel, that's cool. All right. So in the next section of notes, it says, use the slope-intercept form of the equation of the line that passes through the points. Use a graphing utility to graph the line. You guys feel like you want to see an example of that? Or do you feel like, I got that? So you basically what this means, that's a bunch of words, but we need to find the equation that goes through these 2 points. If I asked you to do that, do you feel like you could, or do you want to see an example of how to do it? Nobody wants to tell me either way. I think I'm going to go ahead and do this one because I know that a lot of times this is a kind of a question they like to ask on the ACT. So they like to give you 2 points and then ask if you can figure out a line that goes through those 2 points. Awesome. All right. There we go. Don't save that. Oh, somehow I opened a spreadsheet. Okay. All right. Let's talk about getting 2 points and figuring out the equation that passes through these 2 points. So this is on Monday. We reviewed this thing called the slope-intercept form of the equation. And that's one possible way to find the equation that goes through these 2 points. And then there's basically two possibilities. Everybody loves it when there's 2 possibilities, right? Totally. Okay, I did something wrong here. Let me see. I think I opened my thing in a spreadsheet somehow. Open in Paint. That's what I was going for. All right. So let's do number 38. Okay, so you have a point at 1, 1 and a point at 6, -2/3. And we want to figure out the line that passes through those points. So we know that the line is going to be in this format, y equals mx plus b. Anytime you have a line, it can be written as y equals mx plus b. Any line, any linear equation can eventually be written as that. But we have 2 points. We don't know the slope or the y-intercept. So how are we going to do that? So I'm going to go ahead and do it the way that I remember because that's the formulas that I know. And then I'm going to show you the other way too. Okay. So the first thing that I need to tackle is the slope because I can't really figure out the y-intercept unless they give me a point, or maybe I graph it and it looks clear to me, but can't really do that. So I know that I can find the slope when I have 2 points by using the equation. The slope is the change in y over the change in x, or y2 minus y1 over x2 minus x1, right? The slope is just the change in y over the change in x. And I have 2 points, so I can figure out how does it change, right? All right, we're going to make this our x1, y1, x2, y2, right? Okay, so my slope is going to be, sorry, number 50, I'm going to write over here. My slope is going to be negative 2/3 minus 1 over x2, which is 6 minus 1. Okay, negative 2/3 minus 1 is actually, I'm going to do a little math magic here. It's actually negative 5/3 because you change 1 to 3 over 3, and you get negative 5/3. And then 6 minus 1 is 5. So how do you deal with a fraction that turns out like this? A fraction with a fraction. This isn't proper math. Everybody's like, ugh. Remember, another way that you can think about this is you can take the numerator, okay, and you can write it as 5/3, and the denominator is 1 over 5. So the slope is 5 over 15, or negative 1/3. So our slope is negative 1/3. Remember, we started off up here trying to figure out slope, negative 1/3. Okay. So now we have our first part of the equation, right? We know that y equals negative 1/3 x, right? Plus b, but we don't know what b is either, right? B is our y-intercept. How do we figure out what that is? Well, in order to figure out b, we can plug in some x and y, and then we could get b all by itself. Where in the world could we find a x and a y that works for this equation? Oh, right up here, we have 2 sets of x's and y's that work for this equation, right? Let's maybe use one of those. I think I'm going to use the first one because the numbers look a lot easier than multiplying by fractions, but I think either way you'll end up with a fraction. So you can use one of these and say, oh, well, if this equation is true for my line, then it should work for 1, 1. So when y equals 1, you multiply by the slope, and then you plug in that x equals 1, right? You could also plug in 6 and negative 2/3, and this would work the same thing. Same way, not same thing, same way. Okay, so we have 1 equals negative 1/3 times 1. And then if you do math, I'm going to kind of skip a little bit so you don't have to watch me subtract fractions. You get b equals 4/3. Okay, 4/3. Yikes. Okay. So now I've solved for my slope and I've solved for b, and I put them all together, and my equation is y equals negative 1/3 x plus, I need to get my pen out because I'm clicking too much, 4/3. So this is my equation of the line that passes through those points. Now, if I am taking an ACT or SAT test and I'm in the calculator section, how do I know that this is right? I can graph it, and if I made my equation of my line correct, then these 2 points should be on my line. Okay, so again, switch back to Desmos, and my equation was y equals -1/3 plus 4/3. And then I got an extra number in there. There we go. So if you remember, one of my points was at 1, 1. So 1, 1, that works. The other point was at 6, -2/3. So 6, -2/3. Oop, almost there. Maybe. 6 and then -2/3. 2/3 is 0.66666. Okay. Is that in your brains back in there somewhere? How was that exciting example?
It kept me on edge.
It kept you on edge, Josiah. You were like, what's going to happen next? Okay. Did that make sense to everybody, though? You're like, oh, yeah, I remember doing that. That was fun.
Yippee.
Yippee. I like to hear that. Okay. The last few problems have to do with something we talked about right at the end of class. I think, yeah, it was right at the end of class. And that is, not only do we need to know about the slope of the line, but how do we know if two lines are parallel or perpendicular? So remember, parallel is the easy one, right? Parallel lines have the same slope. Perpendicular lines have negative reciprocal slopes of each other. So that's how we can tell. So let's do, well, let's talk about a problem or two, and then we'll do a problem or two. How's that sound? And then we're getting there. Okay, so in example number 64, it says, the lines are parallel. Find the slope form of the equation of line 2. Okay, so line 1, and these are the type of questions I know that they like to ask around slope with those SAT, ACT stuff. So make sure you kind of pay attention to these, right? This slope comes back in there. So these lines are parallel, right? Line 1, y1, is -2x plus 1. So what do you know that the slope of the second line is?
A -2.
-2, exactly. So if you know, I keep forgetting I can't write on here. If you know that that's -2, then you know for your second line, right, y2, the slope in y equals mx plus b is -2x plus b. Now, what is the y-intercept? The y-intercept is where the second line, right, intercepts y. And that looks like it's at -1, right? So we could say that y2 equals -2x minus 1, or plus a -1. That one's pretty easy. We like perpendicular lines. They're pretty easy, right? Or perpendicular. We like parallel lines. They're pretty easy. The slope is the same. All right. What about this guy, though, that's perpendicular to each other? Yeah. Right? We're trying to figure out what our equation of our line is, right? So we want to know what y2 equals mx plus b. What is easier to find here, the slope or the y-intercept of y2? Which one's easier to find? I say the y-intercept's easier to find, right? The y-intercept is right here. So the y-intercept is at 4, right? How do we figure out what the slope is? Well, the problem tells you that they are perpendicular to each other, right? So that means they're at a right angle. And that means that the slope of my first line is the negative reciprocal of the slope of my second line. So the slope of my first line is what? It's 3, right? So the slope of my second line, M2, is negative 1/3. So not too terrible, right? So my equation of my line would be negative 1/3 x plus 4. Yep, Greta texted me. I just saw it, Greta. Yep. Okay, so don't forget that relationship. There's a couple more examples at the end. Not too awful, that's right. There's a couple more examples at the end where you have two sets of points and you have to tell if they are, here, let me just pull it up instead of talking about it. These last few problems, I think you just have one problem out of there, is to tell whether these two lines are parallel, perpendicular, or neither. So how would you do that? You have to find the slope of the first line and the slope of the second line and then compare and say, are they parallel? They're parallel if the slopes equal each other. Are they perpendicular if they're negative reciprocals, or they could just be neither? You can also graph these. You can always graph them to make sure that you're on the right track, right? It's always a good kind of second look. Okay, so that is 1-1. So you guys can go ahead and tackle the homework. It's right there at the top. It's 1 through 23 odd, 33 through 49 odd, and 53, 55, 63, and 65. So I know it seems like a lot, but I think a lot of them, once you get into them, some of them, it's just you look at it, you write it down. There's just a couple that'll take a little bit more work to get through. All right. Now I want to talk about something very exciting, which is called a function. So I know that we spend time on this in Algebra 1, and we spend time on it in Algebra 2, and guess what? We spend time on it in pre-calculus. Okay, so dun dun dun, just keeps coming back, right? This also is an important test question that they like to ask about. What makes a function different than a relationship? So a function is a specific type of a relationship. And it has one particular rule, and you can kind of see I've obviously copied out of your book, but I'm going to kind of paraphrase it for you. Okay, so a function is when you have a relationship between two things, and to each value of the independent variable, there corresponds exactly one value of the dependent variable. Okay, so let's kind of break this down a little bit. Okay. What you put in is your x. So let's print screen this. So obviously you guys can read what the summary of a function is, but I just kind of want to break it down into, let's make sure we really, really understand what's going on with the function. Okay, so the first thing is when you see a function, it's f of x instead of y. Remember, f of x acts just like y, but this notation tells you, yep, we've got a function, right? And in order to be a function, what you have is you have some set of things that you put in, right? And that we call your input. Has a couple different names. You put it in, it has your input. Usually we put in x, right? Some x's, x1, x2, x3, etc., right? And this is called the independent variable. So instead of you guys watching me write independent, I'm just going to make my squiggly line there. Okay, it's independent. So that makes sense, right? If you are working with a function or an equation, you can pick you know, you have y equals mx plus b, you can put any x in there and kind of figure out what the y is going to be based off of that, right? That's what you put in. Then you do something, it goes through this function, right? It goes through this function. And then on the other side, we get something out, which we can call the output, right? Usually what we get out is some y, right? y1, y2, y3, okay? And this is called the dependent variable. So y depends on what x you put in, okay? So that's kind of how we think about a function. The one rule with a function is that for every sorry, I'll make sure I say it right. For every independent variable, okay, there is only one dependent variable. So instead of talking in theoretical, that means if I put x equals 3, okay, if I put in x equals 3 in my function, I only get y equals 5. Okay? This is the relationship that makes it a function. If I put in x and 3, x equals 3 every time, I'm going to get y equals 5 or whatever that answer is through the function, right? What makes it not a function is if I put in x equals 3 and I can get y equals 5 or y equals -5. This idea that I put in one input and I could get two different outputs makes it not a function. Okay. So it's up here, it says, for each value of the independent variable, there is exactly one value of the dependent variable. So it's a one-to-one relationship between the independent and dependent. Okay. Another way that, and I don't think your book talks about it, but another way that you can think about this. Oh, well, let me take a step back. What is okay and does confuse people sometimes is that, let me just put up a set of numbers up here. Okay. So say my x's are 1, 2, and 3, super fancy, right? And my y's are 5, 6, and 7. So if I put in 1 and get out 5, yes, I still have a function, okay? I put in 2 and I get out 6. Yes, I still have a function, right? I put in 3 and I also get out 6. That's okay. I can actually put in 3 and get out 6 because I'm still, when I put something in, I only have exactly one answer, right? Where it goes wrong is if I put in 3 and I can get out 6 or 7, that's when I no longer have a function. So the input having more than one output is where you no longer have a function. All right. Two other things I want to point out. We just want to add extra names to everything, right? So another name for what we put in or our x's or our independent variable is our domain. Okay. And the domain is all the values for which we can put in. And a lot of times the domain is all real numbers. We can pick any real number and put it in, right? But sometimes there'll be a restricted domain to what we have. And then what we get out, right? Our dependent variable is called our range. These words all coming back to you? Okay. So we have our domain, our range, domain input independent, range is our output, and it's dependent. The function has to have, for every one thing you put in, has one thing you get out. It's okay if what you get out is shared with another value, what you put in, but it can't go the other way. The last little thing that I don't think your book explicitly covers, but I did want to mention, is that one way to check. So one way to check is to look at all your values and see if you have any that overlap. And I think we're going to do that in some of the examples. Yeah, there's a couple examples there that you can do that. Another way that you can check is called the vertical line test. So think about if you graph a function. Okay, so if I graph a quadratic function, and I know we're almost done, that's why I'm just doing this at the end. If I graph a quadratic function that looks like this, anywhere I draw a vertical line, there's only one answer. So that means if I put in this x, I get this y out. If I put in this x, I get this y out. Some of those values are shared, but that's okay. If I graph a quadratic function that opens this way, which we talk about in Algebra 2, and we'll talk about, I think, this year. Yeah. If I graph, whoa, that's crazy. If I graph a if I graph an equation that looks like this is not a function. Because right here, say this is x equals 3, right? My answer could be y equals 3 or y equals -3. So visually, this vertical line test is one way to tell if you have a function or not. Sometimes you just have to look at the numbers and see if you have a function or not. Sometimes you have to just kind of dig into the data to figure that out. So we just started that. If you want to try any of the first few problems, you can definitely try, like, 1 through probably 1 through 7, 1 through 9, something like that. That's just looking at the numbers and seeing if they're functions or not. All right. Very exciting discussion of functions this morning, right? I'm going to go tell your family and friends about the excitingness. Yep, that's right. Awesome. Well, thank you guys so much for joining. Oh, I was going to say at the end, let me know, send me I'll stop the broadcast so it's not broadcast. Send me in your chat